we have not covered. Yesterday we have not covered the odd ratio and relative rates. Today we will cover this portion, odd ratio and relative rates for comparing the two proportion first, and then we go for the pair design. How to calculate the sample size for the pair design uh, for mean and for proportion.
So, are you muting?
There is disturbance.
Yes. So now you can unmute, sir.
So then after that, we will discuss about the sample size for agreement between the two variables, continuous or categorical, for intra-class correlation and kappa statistics. Then I will tell about the some of the strategy to reduce the sample size. How can you reduce the sample size and then how to correctly account the loss to follow up. There is a common mistake of the students in doing calculating the loss to follow. There is one example I will show that one, and why. Then we will discuss why we not calculate the post hoc power calculation, and then that online calculator we will use for finding this sample size with the example. So first of all, I will explain about the case control design for calculating the sample size based on the odd ratio. We use the study design as a case control. Now in case control, what happen is that you all know about, but I am just describing a recap for that. In case control study, we first find the cases and control, and then we go to the back of that. What is the out of the case, how much is exposed and how much are unexposed? Similarly, in the control group, exposed and unexposed. So this is the direction of the case control. On the other hand, if we go for the cohort study, then we have exposed group and unexposed group, and then we follow for the certain period of time, and then we find the disease and non-disease. So here the difference is in cohort studies we found the relative risk, and case control study we found the calculate the odd ratio of that. So this is the one example I am taking. So this is the one example is that this is exposure and disease, and exposure is my smoking and disease is MI. So I will go for the relative risk using cohort studies. That is means we follow the smoker and non-smoker for the certain or period of time, and then we find what are the MI. So how we calculate the relative risk? Relative risk is the incidence of disease among those exposed. Incidence of disease. Disease here is MI is disease, that is 355, those who are smoker, divided by total number of smoker, how much is there? That is 355 plus 314. So this relative risk is 1.92. Incidence of disease among those not exposed. So that is equal to C divided by C plus D. So our relative risk is that the person got MI among the disease divided by among, one second. The relative risk is that risk is that A upon A plus B, that is the incidence of disease among the exposed divided by incidence of disease among the not exposed. So when we divide this, we find the relative risk. That is A upon B divided by C upon D. So this is our relative risk. On the other hand, we found the odd ratio. Odd ratio is that we know about the MI, and then we go for back of that which persons of MI are smoker and which are non-smoker. So the odd ratio is equal to odds of people with disease being exposed divided by odds of people without disease being exposed. So this is the odd ratio for that. So A by C, this is 355 divided by 140, 355 divided by 140, and 3140 divided by 2507. So odd ratio has a benefit of that. If you see that odd ratio can be calculated by cross multiply that B by C divided by A by D. So there is a formula for calculating of odd ratio. These are the meaning of the odd ratio and relative risk. Relative risk found that if those person who are exposed, how much risk is increasing due to the exposed on disease. Similarly, odd ratio we found that with the disease being exposed and without the disease being exposed. So if you have a relative risk and odd ratio, how we calculate the sample size. So this is the thus brief of the what is the meaning of the relative risk and odd ratio for your understanding. Now we come to the formula for calculating of odd ratio with equal number of cases. Here the odd ratio is odds of exposure in case divided by odds of exposure in control. So this is the odd ratio, and we test the hypothesis of odd ratio is equal to 1. With alternative hypothesis, odd ratio is not equal to 1. That means it may be greater or it may be lesser. For the two-sided and one-sided, it may be greater only or it may be lesser only. This can be transformed into the proportion using the following formula. So we can transform the odd ratio into the proportion of one group into proportion of two group. Yesterday we learned about this formula. This is the finding out the proportion of the two groups. So we convert the odd ratio into the proportion of 1, proportion of 2. What is the given? Given you have to know about the what is the exposure in control group and what is the odd ratio. This you have to find out from the previous study. You find what is the or what is the proportion of exposure in case. So this is pi 1 and this is P1 and P2. So same formula we are applying here to find out the sample size in case of odd ratio, because we have converted the odd ratio into the two proportions. So this formula is you have to remember for converting this one. So one example I am taking that the investigator plan a case control study to see the effect of influenza vaccine in preventing COVID-19 among the health worker in COVID-19 18 dedicated hospital. So he want to know about the what is the role of influenza vaccine in preventing COVID-19 in the health worker. So investigator expected that 70% of non-COVID health worker are vaccinated with influenza vaccine and expected that odd ratio of 0.5, that is a preventive. We are assuming that their influenza vaccine is preventing the COVID. 0.5 with 80% power and 5% level of significance. So this is the question is that then how large a sample size is needed? So first is the P1 is exposure, influenza vaccine among the cases. This we have to find out. What is the given? P2 is given, exposure, influenza vaccine among the control. That is 70% we have given. We calculate the vaccination effect in the case. So there is a preventive effect is there. So among the control, it is a high, and in among the cases, it will be low. So using this formula, converting this formula, that formula I have, this formula you see that OR multiplied by pi 2 plus 1 minus proportion to bracket OR minus 5, 1. So here you can use this formula for calculating this value. I think with the, okay. So this value you find out the 0.538. Now we have a proportion of 1 and proportion of 2, we just simply applied this formula to get the sample size. That is, yesterday I already explained to you the for the proportion of 2 for comparing the 2 proportion. So first we find out the pi bar, that is a sum of 2 proportion. This is 0.62 and substitute in this formula 1.96, that is our confidence level at 5%, well, Z value. 2 multiplied by 0.62, 0.38 plus 80% power, and this is our pi 1 0.538 multiplied by 0.1 minus this one, or 0.70 multiplied by 0.30 divided by difference of this. So if we substitute in that, you get the value of 140. So 140 cases and 140 controls are required for this question, to answer this question. So this is about the, if the odd ratio is given and it is given the what is the expected value in the control group for exposure, you can find out the value, sample size for the 2 proportion. Now, this is another example I am taking for the odd ratio to better understanding for that. So investigator plan a case control study to see the association between the malnutrition of the cyber palsy and cyber palsy. So they are finding the association between the malnutrition and cyber palsy. The previous study reported that the odds of malnutrition in cyber palsy children is 7.8 compared to control. So this is the previous value are there 7.8, but the expected proportion of malnutrition in control is 21.6 and odd ratio malnutrition in cyber palsy is 3 as compared to control, which to have 80% chance to detect whether the odd ratio is significant or not. Here he assumed that the odd ratio is 3 to 4 sufficient for finding the difference. So here the malnutrition among the cyber palsy children is equal to malnutrition among the cyber palsy children. Okay, among the control. This is among the control. I have written wrongly. Malnutrition among the control is equal to 0.216, and then I use this formula to find out the malnutrition among the cyber palsy children, that is equal to 0.453, because it is odd ratio is 3. So in that case, it is greater than control. Now we add then this pi bar to calculate the overall value, average value of this 0.335 and substitute in this equation. When you substitute in this equation, the answer will come 63 children in control or 63 children of cerebral palsy is required for this. So this is about the odd ratio. Now we come to the finding out the how to calculate the sample size in case of relative risk. There is a difference between the relative risk and odd ratio. Relative risk we generally directly compare in the number of times, how much times it is increasing. Odd ratio is not number of time. So in relative risk, the proportion of disease in exposed population divided by proportion of disease in unexposed population. So we compare the test hypothesis relative risk equal to 1 with alternative relative risk not equal to 1, that may be greater than and less than. And similarly here also we need the proportion of disease in non-exposed population. Or what is the anticipated relative risk? So using this formula, because relative risk is equal to pi 1 divided by pi 2, directly you can find out pi 1 is equal to RR is equal multiply by pi 2. So using this formula, you can find out the pi 1, pi 2 is already given to you, and use this formula to find out the pi bar, and then same formula you can use for relative risk also for calculating the sample size. So now I will take the one example for this one. This example is a RCT example. Two competent therapies A and B are treated breast cancer are to be evaluated in a clinical trial in a stage of 1 and 2 patient. So we are taking the breast cancer patient of stage 1 and 2, and patient are randomized into the 2 groups and follow for the recurrence. Here we are finding out the recurrence of disease after the 5 year. They follow up to the 5 year and find out what is the recurrence of disease. How many patients should be studied in each group of trial to be 90% confident of rejecting null hypothesis R is equal to 1 in favor of alternative hypothesis R is equal to not equal to 1 with 95% confidence level. A reduction in the recurrence using treatment A with a relative risk of 0.5. So there is a reduction of using the new treatment by 50%. And expecting the recurrence after the 5 year of treatment B is 35. So in that case, what is B treatment is a old treatment 35, and now we are expecting new treatment will reduce the recurrence by 50%. So our recurrence in treatment A is 17.5%. That is a half of this one. Now again we calculate the sample size. Average of this 0.35 plus 0.175, that will give a 0.2625. So we have a value of pi1 and pi2 and also average value. Then we substitute these values in this equation and then find out the sample size of 131. So this is the sample size of 1,3. Now there is a chance of 25% loss to follow. So in that case, we increase the sample size by 131 divided by 1 minus 0.25, that is 175 per group is required for this sample, this study. So this is all about the how to calculate the sample size of the two proportion in case of odd ratio and in case of relative risk. Now I go to the calculator to find out how to use the calculator for finding out the sample size. Dr. Dharmender, you can see this screen? Hello?
Sir, it is visible.
Acha, theek hai. Now we find out from the odd ratio. Same statulator we are using here. In statulator, we go to the sample size and compare to the two independent proportion. Like yesterday we did about that. Now, what is the input we have to give? Expected outcome proportion in the reference group. So reference group, I am giving the, suppose I am giving the reference group as a 40%. Now I click on the measure of association. Here my measure of association is odd ratio or relative risk. You can select odd ratio or you can select risk, relative risk depending on your design of the study. You are using case control study or you are cohort study you are using. So in case of suppose I am using cohort study, so put the relative risk. Then you have to put here the relative risk value. What is the relative risk value? If it is greater than 1, you are right. Greater than value 1.5, 1.2, whatever you are taking for the relative risk, or it is less than, you can write the less than. In case of I write 0.5 here. So this is my relative risk reduction in the treatment. So then I go for the adjustment. Adjustment is applied for the continuity correction, adjustment for the clustering, and adjustment for the response rate. You all know about what is the meaning of that. So I am uncheck this and update. And then I calculate this. So this will give the sample size of 79. So assuming 40% subject in the reference population, that is control group having a factor interest, and reduction of relative risk of 0.05 between the two test reference group at the two-sided point p-value at 0.05. So if I increase this to suppose 2, so in that case my sample size will be 2. So you can play with this software for the finding the different relative risks, or you can directly visualize this table, visualization or table. You can go for this table and you can find out that on the different expected proportion, and this is the reference. What are the value of your sample size? So, but in that case, RR is not given. So you have to calculate what is the proportion in that pi 1 you have to calculate on the basis of RR. So this is not giving for RR. So you have to calculate. Suppose if you have a 0.4 or my odd ratio relative ratio is 2. So I go for this 0.80, that is 20th. So in that case, you can directly calculate the this test proportion based of relative risk. Now we come to the odd ratio. If you are same, you are taking 0.4 and you click on the odd ratio. So this you click on the ratio and then calculate. So our sample size will increase from the adjustment. I will no adjustment. So sample size will be 130. So you can see that how the changes in the sample size for the relative risk and odd ratio. There is a difference for coming depending on your study design. So there is a difference of that. So now I will take one example of this. Again, it increased to the proportion to the 0.6. So you can see that on the odd ratio, the sample size is 150. So as the proportion is increasing, odd ratio remains same, the sample size is decreasing for that. So this you have to can see that for what reference value and odd ratio, the sample size is increasing or decreasing by playing this software. I hope you understand the meaning of the odd ratio and relative risk, and now this calculator you can easily use. And if you want any adjustment for this one, continuity correction, adjustment for clustering, adjustment for response, you can update that. Another option is that in a case control study, you have an option for selecting the ratio of that. So in that case, you can select the 2. So this is one calculated 1:2 ratio. So now it will increase 108 for the one group and 216 for the another group. So here you can change the ratio of the group also. In case group is 1 and control group is 2. And another, if you are increase the power from 8, you can increase the power from 80% to 90% by clicking this. So your sample size will increase. When you increase the power, your sample size will increase. So that is the, you can find out different ways of combination for finding the exact sample size using odd ratio and the relative risk. Now again we go to the pair design. What is the meaning of pair design here? So pair design is one. There are different conditions where we use a pair design. Pair design example of I am taking before and after intervention. You are taking one group of that. One is before treatment you are taking, and second is value you are taking after treatment. So you want to find out what is the effect of treatment. Although this trial is one group trial is not good, but somehow you in some cases you don't have any option, but you go with the one group of that. So that is a before and after trial, before and after treatment it is called. Another method of pair design is, suppose you are measuring the variable by the two methods. So that method is a manual and digital. You want to compare whether there is significant different or not. Another method for the pair design is one-to-one matching. One-to-one matching means case control. You all know about that. Case control study is observational study and bias due to the confounders. So if there are known confounders are there, you match that known confounder by one-to-one matching, or you can make a model for the propensity score. Their model is it. According to that, you can match the case control study. If there are 2 or 3 confounders are there, so you can match the case control based on the 2 or 3 confounder. If you have a more than 2 confounder, then you can go for the first make the propensity score modeling, and then according to the model you can match the case control patient subjects. Another is a analysis of paired organ. So if you are going to be analyze pair organ of the same patient, like one eye you are giving the another treatment, or one you are suppose one eye you are giving the treatment and comparing the with the control, second eye as a control, same of the ear. One year you are giving the treatment, or second year you are making as a control. So same for the kidney. So the different pair organs are, if you are comparing, that is also called a pair design. Another design is a split mouth design. A split mouth design we use in the dentistry, where we divide the mouth into the 4 part: upper jaw, lower jaw, or right jaw, or left jaw. So in that case, we give the one treatment, left treatment, another method, another left, suppose left jaw, alag, different treatment, and the right jaw, there is a different treatment, or then you compare whether there is significantly different or not. So that is called a split mouth design. So these are the example for the pair design. You can find out in case of this type of design you are facing, then how to calculate the sample size, we will discuss about that. So this is the one pictorial example for the single group before and after, that I like. Before treatment you are before, and after you have taken the sample and well recorded the value, and then after you are giving the treatment, and then there is a after treatment you are recording this one. The second is a two group matching design. In two group matching design, participant is this one. There is a number of participant is the first you match the pair, like in countryman I have told the case control study, you match with the number of confounders. So they have matched with the number of confounder here. That blue is one confounder, that case control is this. Then you give the one treatment to another and second treatment to the other group. So in that case, two group matching design is this. This is the two group matching design. So this is the some example for that. Now we come to the how to calculate the sample size for the one group before and after study. So this is the formula for calculating the sample size for the pair design for continuous variable. So in continuous variable, we need the standard deviation of change. That is the standard deviation of D, means standard deviation of change before minus after, and how much difference you are expecting of change as a clinically important difference, that is called delta. So this is the in before treatment and after treatment, how much change you are saying for the clinical important. Then this is the same level of significance, and then it is a power for that. So, but problem is that in pair design, you don't know about that. There is not much information available for the standard deviation of change. Generally, in article, you don't find the change standard deviation. So how you can compute the change? That is the formula for calculating the change on the basis of pre-value of standard deviation or post-value of standard deviation. So in that case, we assume that this is the standard deviation of before, standard deviation of after, minus 2. This is correlation between the pre-value and post-value. This correlation is also not available in the previous literature. So the rule of thumb for making is that you take 0.5 as a correlation. You can increase or you can decrease, but a rule of thumb is 0.5. If correlation is there, then you can take that correlation. Otherwise, you generally we take as a 0.5 for finding out the change standard deviation. So you can use this formula for calculating the change and substitute here to find out the sample size for the pair design. Here the null hypothesis is that there is a no difference in pre and post value, and alternative hypothesis is that there is a significantly different then 0. Significant difference is that there is a delta value that is clinically important difference. So that is greater than 0 or in positive direction or in negative direction. That is two-sided. It may be less than or it may be greater than depending on the your what is your outcome. Your outcome is a good outcome or your outcome is a bad outcome, or higher value is better or lower value is better. Or there is a one-sided tail also. One-sided, you can say the pre minus post is greater than delta and pre minus post is less than delta. That is one-sided. If you are 100% sure that my treatment will either reduce for the value where reduction value is a good value, or increase the value where the increased value is a good value. So in that case, you can take a one-sided design, one tail design. Then higher the correlation between the pre and post. If the correlation is higher, what means is this? This is a subtracting term. You are subtracting from the variance so that if this value is correlation is higher, so you get the small standard deviation. That means it's lower variability. If the correlation between the pre and post is higher, in that case, you have a lower variability. Lower variability means there in change, the variance is less. In that case, you get the small sample size. On the contrary, if your correlation is 0, suppose if you put the correlation is 0, in that case, this is our standard deviation and you get the maximum sample size for that. So minimum sample size you get in if you are it is 1, or maximum sample size it correlation is 0. So this is a method for the calculation of the sample size based on the before and after design. So I will take one example for this to explain. Investigator want is planning to assess the 6-minute walk test for the MI treatment patient within the 7 days and after 1 month of follow. A patient has MI and it is treated, and there is a 6-minute walk to assess their quality of life or as of the treatment of MI. So 7 days and after 1 month, they are assessing the 6-minute walk of the patient. The previous study shows that the standard deviation at 7 days and 1 month is equal to 85 and 103 meters respectively. If a change of 30 meter is considering a clinically important difference. Now here, if we see the 30-minute change in 7 days to 1 month of the patient is considering as a significant improvement, how big a sample size is required with 80% power and 5% level of sagging? Considering the one tail, or we can consider the two tail also situation. Assuming the correlation between the pre and post 6 walk is equal to 0.07. Here we are assuming the correlation is 0.077. But if you the rule of thumb shows that if there is no information of correlation is available, so you can take a 0.05. That so SD is of 7 days is 85 meter and SD of 6 months is equal to 103 meters and correlation is 7. One tail value is equal to 1.645 and two tail is 1.96. So this is the formula you can substitute. And how to calculate the change? Change you can calculate change of standard deviation equal 85 square plus 103 square minus 2 multiplied with 0.7 multiply by this one 85 and 103, that gives the standard deviation of change is equal to 75.6. Then this is the change you can substitute in this 75.6 squared multiply by 1.696 plus 0.84 divided by 30 square. So this will give the 50 MI patient. So in 50 MI patient you will take to prove that there is a 30-meter change for the one tail, two tail. And for the one tail, you need 40 MI students, MI subjects. So there is a difference of 10 MI subject for the one tail to two tail. So this you have to care whether you are going for the one tail or whether you are going for the two tail. So this is about the sample size calculation for the pre and post well for one group. And for the two groups, there is a complicated. Now, I am not covering that part. That is a called repeated method ANOVA or some in the two groups, whatever you can calculate the change. If you have a two group, then you can calculate the change, and on the basis of change, you can calculate the sample size for the two means according to the two means. So that is the way for calculating for the two groups. If you have a more than number of time of a measurement, in that case, you need a repeated measure ANOVA. That ANOVA, that is a complex procedure for that, for calculating the sample size. So we will discuss in next webinar for this one, how to calculate the sample size for this randomized repeated measure ANOVA. Now we come to the how to compare the sample size for the proportion in the two groups. So this is the some complex procedure for that. So I have tried to explain what is the meaning of the proportion, how to calculate, but there is some complex. I may doubtful that you may understand it, but I am trying to explain as I can explain that. So there is a in a proportion, there is a match study. What is the match study? Is that we match one group of patient to the another group. So for example, I am taking here the simply cold and cough. So those person who are taking the cold and cough match with the other person or same cold the disease for cold and cough. One group are taking the treatment and one group remaining that they are not taking any treatment. So we are finding that is matching is with the age, sex, BMI. So this is the example I am showing that one. The study of therapy in relieving a common cold with 1 week. The researcher planning to do a case control match study with the age, sex, and BMI. So he three factor he has matched. Okay. Now we come to this match. One group is taking the therapy, another group is taking control. They are making no therapy. So total number of n pairs here, n is equal to n pairs are there. So n pairs, this is 2 by 2 table that therapy relieved. Those who are taking therapy, they are relieved. Those who are not taking any medicine, they are also relieved. That is called A. That it means relieved by either by therapy, both therapy and the control. So these are the pair. You have to see this one. This is the A is a number of pairs. Number of pairs means one pair, one patient of therapy group, one patient of control non-therapy group. So A is a number of pair. So B is also number of pairs. That B means those who are relieved by the treatment, but corresponding subject, that math subject is not relieved by the control group. Control group. So they are those who are not taking the therapy, that is not relieved. They are of corresponding pair. So B pair, some are relieved or some are the B pair, B is relieved and the same pair of that is not relieved. So C is what? C is the number of patient, number of pair that is relieved by control group, but they are not relieved by treatment group. And the D is that is not relieved, number of pairs that is not relieved by therapy also or not relieved by control. That is number of pairs. I am again repeating, this is the number of pairs. So one pair taking therapy, another corresponding matched pair is taking not therapy. So the D is number of pairs. So we can, this table across 2 by 2 table are there. Then we understand this table and then we calculate our That's good. Uh, Now we have to find out the what is the value of pi. Acha, one thing more I have to explain. This relieved into relieved and not relieved into not relieved, A and D are called concordance. They are agreeable by the both pair are agree by the treatment and the control. Discordant are the B and C. So we consider the only B and C for finding the sample size because they are discordant. Discordant means some B pairs are relieved by the therapy but not relieved by control. C pairs are relieved by control and not relieved by therapy. So which one is higher group? We compare that B versus C. So this is our null hypothesis for this discordant pairs. So we use this as a null hypothesis for. So we calculate here the pi 01. Pi 01 is what? C divided by N. So this is the C number of pairs divided by total number of pairs. So C divided by N. This is C divided by N. Now we go for the pi 10, that is B divided by N, or this is the therapy effect B A plus B. A plus B divided by total A plus B number that is relieved by treatment, and this is pi C is that number that is relieved by the treatment. So if we subtract that, pi t minus pi c, that is give is equal to pi 10 minus 0 pi. This is our concordance pair difference, that is B minus C. This is B minus C. Now, B number of pair by C number of pair. So this is our hypothesis for comparing this. Now, this is some complex formula for calculating the pair design, because pair design have a correlated design. So there are the complex formulas for calculating. Maybe I think you are not able to understand this one. So I think we will go by the calculator. That is the better way for understanding this. But uh, although I explain this formula, because if I am not explaining, then you're not able to find out what is the input you have to give. So this is the formula you have to calculating for the pair. The pi 10, we are taking only here the discordance pair, not discordant pair. So only on the basis of discordant, because we null hypothesis that there is a there all the uh, discordant pair, that B versus C, this B versus this C are equal. So this 1 pi 10 equal to 0.1. That is both are equal. And our alternative hypothesis is that discordant pair are different. So to find out therapy effect, now if we want to prove that the therapy is better than the those control group, so in that case our B pairs will higher and C pair will less. So in that case scenario, we say that our therapy is better than control. So these are the this formula, and we can estimate using calculator. You don't, I think there is a difficult. So I explain this using a one example. This example already for the this relieving of common cold. So now in common cold, a difference of 20%. Now don't BK say that if the therapy improved the patient pairs by 20% between the therapy and control is considered a significant difference. So 20%, if the higher is 20%, then we say that it is a therapy is better than the control. The previous study showed that 60% relief by the therapy and the 40% relief in the control. determine the sample size with the 80% power and 5% level of significance. So this is our question. We have given the 60% relief therapy, 40% this one, and 20% consider as our significant difference. But here one thing you have to see that we are assuming here that there is a no correlation between the two pairs. No correlation between the two pairs. If you are assuming the correlation between the two pairs, so you have to give the correlation value. Like in continuous variable, we have taken the 0.5 as a correlation value. Same thing you have here, you have to give 0.5 for the correlation value between the two pairs value. So I will go for the one statulator to explain this. I think that will be the better way for this one. So same way, Dr. Dharmendra, you can see that's in a slide, statulator slide. Hello.
Yes, sir. Yes, we
Huh.
can see you.
Okay.
Can see this.
Then first we go for the compare for the mean. So if you click on the compare of the mean, it will ask the mean and standard deviation of difference. And otherwise it will ask the effect size. So first we put that the mean and standard deviation of difference. So two values it is this software is asking for this one. What is the pair difference and what is the standard deviation of difference? That I say you have to calculate this one. So this is the pair difference. All it is assuming that you have already difference of standard deviation. So pair difference is 20 and the standard deviation you are taking as a 10. Then you calculate the sample size. For calculate the sample size, it is giving the 5. So we can increase our sample size by, if we are assuming that it is a 20, so it will increase to the 11. Now we go for the adjustment. What are the adjustment are there? So same adjustment for the clustering, adjustment for the t distribution. That t distribution I have explained the two sample. So why we take the t distribution adjustment, or so I am unchecked this one. So now sample size is 8. If you increase the standard deviation to the 30, so this calculator will be 18. So for finding out the number of pairs, you need the standard deviation of change and the what is the clinically important difference. But standard of deviation of change is not available. In that case, you use that formula for finding out the standard deviation of change based on the correlation. Now, here one method is that effect size. You generally put the effect size. I explained what is the meaning of effect size. That is the change in the mean difference divided by standard deviation. So there are the different value of effect size are available. You can click, choose this 5 or 0.4 or 0.3 to calculate the correlation based on the effect size. But I don't recommend that one. I recommend this formula to calculate the sample size. You have a standard deviation of change or you have standard deviation of pair, and then calculate the effect size. On the basis of this, you can calculate the effect size. Effect size, how we calculate? Suppose it is pair difference is this 20 and I put here as a 40. So my effect size is what? 0.5. 20 divided by 40. I calculate the sample size, that is 32. This is 32. Or if I click on that effect size and take this 0.5, this also come as a 32. So, but here we are assuming that effect size is 5, but here we have a actual values of this one. So we can calculate the effect size. If you take as a 30, so your effect size is what? 20 divided by 30, that effect size is 0.67. So in that case, you sample size is what? 18. If I put that effect size as a 0.67, so my sample size is equal to 80. So in same, you can change according to the effect size, but my personal opinion is that you use this formula. Now we come to the sample size for calculating the pair design for proportion. When you go for the proportion, so it will ask the two things based on the specify marginal proportions or specify the discordant proportion. So what is the meaning of marginal proportion and what is the meaning of discordant proportion? That I have explained, try to explain. Uh, Marginal proportion is this. If you click on marginal proportion, then expected proportion. This marginal proportion is what? Your PT value, pi t value or pi c value. That is pi t value or pi c value in the equation. This one. I again, actually it is difficult for simultaneously open that one. This is our marginal value. Pi t, this pi t is equal to marginal value, or for treatment group, this pi t uh, uh, now you can this pi t is equal to our uh, now you can see the PowerPoint now, Dr. Dharmender.
No, sir. Yes, sir, we can see.
Okay. So this pi t is our treatment marginal value. This pi t c is marginal control value, and then we have to give the what is correlation value. What is the correlation value? This for one marginal value. For the discordance pair, you have to give the B or C pair of values. That is pi 10 minus pi 01. So whatever information you have available, you can take that information. Now I come to the formula for. So now you can see the formula slide na, Dr. Dharmender. आप देख सकते हैं ना? Hello.
It is a statulator.
Statulator. So,
Yes, it is
okay.
visible.
So this is the based on the marginal proportion. In marginal proportion, you can put the marginal proportion as for whatever I am randomly taking as a 0.4. And this value I am taking the 0.6. One is 0.6, 60% is that. So I am 60% I am taking. And I am taking here 40% for this one. And the correlation value you can take as a correlation value as a 0.3, 0.4, whatever value is, but by default you can rule of thumb say at least you can take 0.5 or 0.24 value, and then you calculate on that. The sample size is 68 based on the marginal proportion. In marginal proportion, you need the what is the total proportion of the treatment group, what is the and what is in the control group, and what are the correlation between them. Then you calculate the formula. Otherwise, you have a discordant proportion. Discordant proportion is that B number of B pair or number of C pair. So what is the proportion of that? So according to that, you can put here value and another value is this one. So you can calculate the sample size based on the discordant proportion. So whatever the discordant proportion you are taking, but generally these proportions are not available in the literature. We use a specified marginal proportion because the proportion are given and you can assume the correlation for this one. So this first formula is generally applicable for calculating this one, but this is rarely applicable if you have a discordance proportion. So these all about that one. Um, this is about the how to calculate the pair design for the proportion for this. So this is only for the one group that is giving the treatment versus other that is case control match studies for the matching studies for that. Or you can find out for the before and after also. Before treatment is what is the status, and after treatment what is the status. So this is calculate for these type, and the test we apply here for finding out whether the difference is that or not. That is McNamara test for finding this. So these are the all about the paired design for the continuous variable for one group, pair t-test, and second is the McNamara test. Now we come to the formula for the agreement method. This is also a complicated formula, but I will try to explain what is the meaning of the intra-class correlation and how you uh, find applicable this intra-class correlation. So intra-class correlation coefficient is there is a difference between the Pearson correlation and Spearman correlation and intra-class correlation. You should aware what is the difference between that. In correlation, we are Pearson correlation or Spearman correlation. We are finding the correlation between the two variables and the two outcome measurements are there, like height versus weight. So there are two variables are there. So in that case, there is a correlation Pearson or Spearman. But intra-class correlation is that if you are measuring the height for before and after, or you are taking the height by the two instruments, manual or digital. So in that case, there are the use intra-class correlation, where outcome variable is same weight. You But in Pearson and Spearman correlation, you have a two different variable, height and weight. So there are two variables. You keep in mind that in Pearson and correlation, there are two variables, two major outcome variables are there. But intra-class correlation, we are assessing the one variable height by the two methods or two ways. So our outcome variable is same. So intra-class correlation coefficient assess the agreement between the two repeated measure of the same numerical variable. That same numerical variable, this is used to find the agreement between the two raters. Suppose a beauty contest is there and there are so many raters are there. So they are rating for the all are the for the same contestant for the scoring system. So what is the scoring system for the beauty? So in our raters are different rater. There are 5 rater, 4 rater. In that case, we find the intra-class correlation whether the raters are agreeable or not agreeable. So, or another example is that if you are measuring the some thickness based on the CT and on the base of ultrasound. So in that case, your same radiology or different radiologies are assessing that CT width and in ultrasound the same width, same parameter width. So in or you can say that there is a stone value. Stone you are measuring through the volume from the CT and stone volume from the ultrasound or from the PET CT. So in that case, you are finding the agreement whether their volume are measuring the same or not. In that case, intra-class correlation we use. Or another example for the intra-class correlation is test-retest reliability. Test-retest reliability is meaning is that if you are developing some tool for the assessing the some outcome like quality of life, pain scoring system. So in that case, first we test and then after the break, we again retest and then find out whether the participant is answering the same question or answer or not there. Or maybe they are to find out whether they are understanding the question in the similar way or different way. If the agreement is not there, that means there is a problem in the question they are assessing understanding problem for the patient. So that is test and retest reliability for developing the tool. So these are the some benefit for the intra-class correlation we use. How we there are different values of the intra-class correlation, but the minimum value of 0.6 is considered as a good for intra-class correlation. So we have to guess what is our expected ICC value and inter-rater ICC assess among the two or more rater. Inter-rater ICC assess a single reliability, assess the similar tool. These are the some examples I am saying. Null hypothesis, we are assuming here the intra-class correlation is equal to 0. There is a row 0. There is some value. generally we take this value as a 0.6 because this is considered as a good, and we want that there should be greater than 0.6 for comparing the control one group. If you have a two group for comparing, then you can go for the uh, row 1 and row 2. But this example I am taking for this one is a row 1 comparing with the whether it is significantly different from the 0.6. So this formula is n is equal to z minus alpha by 2 plus z1 minus beta log C0 multiply by 2k k minus 1. Now here is a k is a number of raters. Number of raters, it should be 2 rater or more than 2 rater. So you have to note down number of raters and then C, how you calculate the C. C is equal to 1 plus k theta 0. 1 plus k theta 1. Theta 0 is equal to kya hai? That is R0, 1 minus R0. Or R0 is my intra-class correlation in null hypothesis, and R1 is my intra-class correlation is in alternative hypothesis, that is row 1 or row 2, row 0 value. So this is R0 and R1. So I calculate theta 0 and theta 1, and after that I calculate this C0. This is the, if you use the calculator, then there is no need for calculating this, but you understand what is the background it is going on. So we need in calculator the number of raters value and what is our expected value of intra-class correlation and what is our null hypothesis intra-class correlation. So these three values we need to calculate for the intra-class correlation. Now I will take the one example for intra-class correlation to understand this. The test reliability of measuring tool of ICC is expected to 0.85. So my this is given 0 to 0.85. The measurement was taken on the two occasion, two repetition, and the lowest acceptable value is equal to 0.7. Now instead of 0.6, I am taking 0.7 as my lowest acceptable value. I need greater than this. And I expect in my study it is 0.85. So how much sample size is required for this? So my null hypothesis is 0.7. Alternative hypothesis are ICC is 0.85 and K is equal to 2. And using, we calculate the theta 0, theta 1, and then C0. C0, it is coming the 0.485. And now we substitute this value into this and get the 42 subjects for proving this study. So we need 42 subjects. So you have to understand what input is required for calculating the intra-class correlation. Intra-class correlation, we need the what is our expected intra-class correlation, what is our null hypothesis, and how many raters are involved in this one. So this information you have to substitute in the software. It will calculate this one. And if you want to calculate by formula, so this is the formula is given, but it is some complex formula is there. That's why you can find out some software. But if you are well in mathematics or calculation, then you can use this calculation and find out the number of this. Now, there is another example for the intra-class correlation. A study was conducted to assess the agreement between the measurement of the tongue thickness by the ultrasonography and the competent tomography scanning. So previous study shows that the ICC between the two methods are 0.95. Expected the similar ICC in our study with 80% power and 5% level of significance. So here you want that in my study is also 0.95. The lowest acceptable value of ICC is equal to 0.85. How much sample size would be needed for 5% level and 80%? So you have to remember that we are going for this for as a one-sided, not going for the two-sided, because we want to find out whether our ICC is greater than 0.85 or not. That is lowest acceptable value. So we are not going for the reverse direction in that case. But if you want to go for say you can go for the two-sided also. So in that case, the number of subject is required 20. Theta 1, theta 0 is 0.85, R1 is equal to 0.95. Alternative, you can calculate theta 0 and theta 1 and then C0 and substitute in this formula, you can get the sample size of 20 subjects. So this is the example for finding out the intra-class correlation for continuous. If you are finding the agreement between the two continuous variable, that is used by the intra-class correlation. One of the method is intra-class correlation. So it is generally used, applied in medical um, statistics or medical researches. So there are another methods are also, but that I am not explaining here. That is a alt blend and altman also. So in that case, you can use find out, but this is mostly applicable in the uh, medical research. Now we come to the agreement in case of the binary. In case some same the binary tool, we use the kappa statistics. You are generally aware about that. Okay, what for the kappa statistics, same for the two rater. It is applicable for the two rater only. So same process is for the like in whatever condition we use ICC, we use kappa statistics to find out the agreement between the two categorical outcome. It may be nominal or it may be ordinal, or it may be have a two category or it may be have a more than two category. So, but condition is that in the both the raters have a same category of that. Suppose if one rater has a 0 to 3, so another rater also have a 0 to 3. It should not be 0 to 2. So on other way, I say ki it should be a square matrix. That means it's in a square matrix is there. So whatever that kappa coefficient indicate the degree of agreement between the two raters measuring the categorical variable. This is used to find the agreement between the two rater, interreliability, consistency. There are so many things are there for binary outcomes for that one. So I am not going same as a intra-class correlation. Whatever scenario we are using intra-class correlation for the continuous variable, you can use for the categorical variable. But condition is that it should be a square matrix, number of categories for the same for the one-sided one group also or second group also. Sometime what happen is that in before and after there are different categories are there. Different categories means in some before you are taking the disease patient, so there are number of categories for the severity or this one are there. But if you are after treatment, the severity gone, so only the mild and moderate is there. So in that case, you have to create a dummy severe column for calculating the kappa value. So that is the analysis part. But how to calculate the sample size for this one? We will use there is a complex formula for that. So I am not explaining that one formula. We go for the samples for web calculator for calculating this one. But I say I explain the two examples for this one, where we use a kappa to better understanding for this one. Two radiologists are study their agreement for the rating of X-ray film for the presence of pneumonia. So their pneumonia is our presence of disease, and the X-ray film are rating for that. X-ray, through X-ray we are detecting the pneumonia, and the two radiologists are independently uh, rating the X-ray film of the patient having the pneumonia or not pneumonia for suspected pneumonia. That it is known that the presence of pneumonia among the patient for the shortness of breath is 30%. That is equal to 30%. P is equal to, sorry, P is equal to 0.3. Now the minimum kappa acceptable is equal to 0.6. The expected kappa is 0.9 at a significance level of 5%. So this is 5%. 5% one-sided with 80% power. How much sample size is required? So in that case, those patients who have a short breathing off, they are suggest for the X-ray and for finding out whether they are pneumonia is there, and that is assessed by the two radiologists. And we are finding that whether the two radiologists are agreeing for the pneumonia or not. This is our question for that. So we have we need the two information, what is the minimum kappa statistics is there, what is expected kappa is there, and the another point we know that the what is the suspected outcome, what is the pneumonia in the short breath patient. So that is 30%. Another example is that two pathologists are steady for their agreement on the decision of malignancy stage of the cancer based on the biopsy. So there are two pathologists are there. So they are assessing the same biopsy of the same patient independently for finding out whether malignant or not. To classify whether they are non-malignant, they are classify the early stage is there, they are classify for the late stage. So there are three classification is there for both the two pathologists. The proportion of malignant in the total biopsies sent by the is 70%. So in that case, this is the 70% malignancy. Those data was sent for the pathologist for biopsy. The minimum acceptable kappa is equal to 0.8 and the expected kappa is 0.9. How much sample size would be needed for 80% and 5% level? So here our objective is to find the agreement between the two pathologists for finding out the malignancy stages of cancer on the biopsy. So this is our study planning for that. So these are the two examples where we use the kappa statistics for this one. Now I come to the calculator for explaining this, how you can calculate for the software. So this software I already told you yesterday to download this one. This is the web software, and here the reliability is there. The reliability, you can click on the intra-class correlation. When you click on the intra-class correlation, it is show the intra-class correlation for hypothesis testing. It is show for the intra-class correlation for estimation. So we go for the hypothesis testing. When you go for the hypothesis, it will ask the what is the minimum acceptable reliability. That is 0. So I told that is you should take minimum 0.60. Expected reliability. What is your expected reliability? Your expected reliability you put as 0.9 or whatever 8.5. And the level of significance. Level of significance here it is taking the two tail. If you want to one tail, you have to increase for two as a double of that. That is 10 for one tail. Or if you are taking two tail, you take as a two tail. And power is equal to 80%. And the number of rater here, the number of raters are 2, or there is a expected dropout. Dropout I am not taking as a, you can take as a 0. If this information you put in that you calculate the sample size as a 26. So my minimum reliability intra-class correlation is 60%, 0.6. My expected in the study is 0.8.5. And I am taking two-sided this one 0.5 with 80% power and the number of raters. This you have to care that if I increase the rater, the sample size will decrease. So that is from the 26 to 18. So in that case, if you are not achievable 26, you can increase the number of rater to reduce the sample size. So that you have to take care about. If you are not sample size is high and you want to reduce the sample size, so in that case, you can increase the number of raters. So that is the for the calculation of the intra-class correlation. And if you increase it to the 90%, so that sample size will increase. As the power increase from 80 to 90, the sample size will increase. Or if you minimum expectancy you increase to the 7, then also the sample size will increase to the 49. So these are the some scenarios you can increase or decrease, or you can find out what is your exact sample size in your study planning. Now, this is for the ICC. Now we come to the kappa statistics. click on the kappa. If you click on the kappa, this is kappa hypothesis, a kappa estimation. That estimation we have no, I think we have covered, not covered for that one. And hypothesis testing, we are covering this. Same minimum expecting kappa is equal to this. I put as a 0.85. And what is the proportion of the p? That is suspected proportion. I told you you have to find out what is the suspected proportion, like in what is the suspected proportion of anemia in the short breath patient. So short breath patient is your target population, and the pneumonia is how much is your disease. So that you have to give here as a whatever value is there, 0.4, 0.5, whatever value you have to give, you have to give. And then the number of drop as a 0, and then you calculate the sample size, that is 84. So in calculating the kappa statistics, you have to give what is the minimum acceptable kappa value, what is the expected kappa value from your trial, and what is the suspected value of disease in suspected target population. Like in, we are expecting short breath pneumonia in short breath patient. So, and then give you alpha level and the beta level. This is based on the two-sided. If you are going for one-sided, you can increase to the as a 1. So it will give the one-sided value. So this is all about the intra-class correlation and the kappa. I hope you understand that one. And now I go about this value. This is all about the interclass correlation, kappa value, pair design. And now there is some error, common error done by the student in calculating the non-response. So you have to check this one. Non-response will be calculated. This new the sample size accommodated with the non-response equal to sample size actual calculated divided by 1 minus what is the loss to follow-up or non-response. So that formula you have to use for calculating this one. Generally, what students do, that I am taking one example to say what type of error they are committed normally. Suppose a sample size is come to be 150. Now you have calculated the sample size, it come to be 150. The researcher expected a 15% loss to follow-up. He said 15% loss to follow-up he expected. Then required sample size is 177 according to this formula. But whatever researcher usually do that 150 and calculate the 15% of 150. That is wrong. And if you add this sample size will come to be 173. So there is a number of 4 subject differences there. So that part is a wrong calculation. Generally, students apply this formula for calculating the loss to follow-up, but you have to do this formula for calculating the loss to follow-up, accommodating the loss to follow-up. That you have to take care while inflating the sample size of by considering the non-response and the loss to follow-up. There is another problem is that some say ki you calculate the power after doing the study. So this is a questionable whenever we calculate the sample size prior to the study and assume the power prior to conducting of the study. There is a no gain in calculating the sample size after the study. When you study and after the study calculate the apply the statistical method and you find there is a significant difference and then you are calculating the power, there is a no gain. Power is directly one-to-one function of the alpha level. So if it is significant, then power is also 80% or it get that greater than 80%. So that is there is a nothing to gain for retrospective power for calculating, and it is also not recommended to calculate the post hoc power for this. In the literature, there is a still controversial, but the most of the statisticians are agreeing that there is a no gain of retrospective power calculation. So this you have to keep in mind. If authors, if you are saying you calculate the post hoc power, so you can say there is a no use for the calculating post hoc power because it is a one-to-one function of the alpha. If it is not significant, then their power is not reducible. There is another issue is that how to reduce the sample size. Strategies to manage the sample size. So there are different type of some are already you know about that. If we reduce the statistical power from 90 to 80%, then there is a reduction in the sample size. The sample size is reduced by 23% if you change two tail to one tail. So but if you are changing from two tail to one tail, you have to keep in mind, you have to defend that one. It will reduce, it will go to the one direction. If you are not sure about that, in that case, you go for the two-sided. Use continuous outcome instead of categorical outcome. Categorical outcome generally give the large sample size. If there are some other continuous variables are available for that one, that is same. In that case, you can use a continuous variable instead of categorical variables. More homogeneous variable, more precise variable, or homogeneous population. If you have heterogeneous population, then in case your standard deviation is more and your sample size will be large. But if you want to reduce the sample size, you consider as a homogeneous population. Homogeneous population means if you find that there is a significant difference of the male and female toward the disease, so you can go for the only for the one gender, male or either female, to make the homogeneous for this one. Then you try to reduce the dropout. Dropout we are taking 25%, but you can reduce the dropout by the some robust method for compliance and all this thing to uh, reduce the dropout. That means you can reduce the sample size. Another is method is that you use unequal group. Unequal group is a, in that case, their allocation. Generally, we take 1-to-1 allocation, but you can increase it to 1-to-5 to gain the power from the unequal group. Increase the minimum detectable difference. In that case, this is not, if you think that there is a clinical important difference, you can increase. So in that case, your sample size will reduce. Use surrogate outcome. Surrogate outcome means you can use the in place of that outcome variable that is highly correlated with your primary outcome. So instead of taking that variable, you can use the surrogate outcome variable. So, for example, I say there is a, if you are taking the pain of the post-operative, then NRS scale is there. So instead of taking NRS, you can go for the what are the analgesic requirement is there. So that is called surrogate outcome because it is correlated with the NRS pain. So that outcome you can use for the reduction of this. Increase the event rate. Event rate, what is the event? This is time to event rate. In survival analysis, we can increase the duration of the study so that we can get the number of event more as compared to if we increase the duration of the study, then event is more as compared to less duration of the study. For example, in cancer patient, we increase the for breast cancer, we increase the study period to 10 years. So we get the more event of mortality or recurrence instead of if we follow up the 5-year one. So that is the one of the method for the managing the sample size. These are the managing the sample size. And now I finish this all the